Hello, my name's Don Smith.
I'm Wes Failer.
We have a volumetric display to show you.
Excellent. Alright, wasn't that cool?
Yes, it was.
Alright, so now we want to show everybody some of the tech details about how this thing actually works. Because we've actually had a few people interested in reproducing the work done on this. And so to introduce you to the core of this, which is a Peggy2LE board from Evil Mad Science Laboratories, I should say, libraries. Edit that out, right? Anyway, so you've got 25 by 25 blue LEDs flashing nicely for us, an Arduino type controller in the background, a nice black, solid black board. You can't see through, despite the fact you could see Don's hand through the back of it. You have some plexiglass to stiffen the whole thing up. It's mounted on some axles, so it'll spin. And it's got some serious lead counterweights up here underneath some strapping tape, and a little counterweighting down here to hold it all together, keep it from shaking too much. And as this thing spins, it drags a Hall effect sensor across these two magnets. One magnet turns the sensor on and the other magnet latches it off. And we can look at the timing of that and figure out how long it takes to do a cycle. And then every time we come through our main loop, we can guess what slice of the real world we're on, and then pull that slice from memory and draw it in 3D space on our LEDs. And then the whole thing is mounted on Don's great idea of a box fan. Tell us a little bit about the mechanics for that, Don.
So box fan, the idea was to have an inexpensive way to build a frame, to construct the frame. This frame is a little light. If I had it to do over again, I would use much heavier construction materials. But it's just very simple, inexpensive angle iron or angled aluminum, and it puts the frame together just fine. It Vibrates a little bit, but with a steady hand and a little bit of weight, helps hold the whole thing down. We're using the rheostat to slow the spin because the standard box fan was just a little bit too fast. Rotate the device so we can look at a couple of the bearings. So at the very top we have a bearing, and I'm not sure if we can see a copper wire. So we have the blue wire, this is plus 5 volts, and then a copper wire as a motor armature that brings power into the Peggy board.
Right. We've got a heavy capacitor on that board, but it's not enough to power it. We don't put batteries on there. So we've got to get power in, and then there's a equivalent one at the bottom, ground, to pull power out.
You should be able to see the white wire is the ground coming over to a copper wire for the grounding wire. This coupling is made out of plastic. This bearing looks like it is metal, but it is mounted onto the aluminum frame with nylon bolts and plastic washer. So it's all insulated from 120 volts, and it's insulated from the 5-volt system.
Right. Now there's another thing with the frame that was important I wanted to highlight. Down here, where there's this little strange cross brace, and that's because we actually had to really take care to secure the motor, to the motor's already secured to the frame, but we found this twisted a little bit. So we had to bend up this really awkward angle piece here just to cut the twisting, and that really made a big difference in the shaking. So a couple notches and a little creative bending and vise made the ever so custom angle on that possible. The corks were just the right height to begin with, so nothing special there. And let's see, what else? Oh yeah, up here, very top, you see the spacer between the board and the plexiglass. We put in a little bit of a spacer, a brace that's a square nylon rod that we use just to brace that, and then all kinds of insulating things, spacers here, so that we didn't actually short anything out. So yeah, this guy does pretty good for us. Oh, yep. Yeah, we just plugged the box fan into our variac here, and then we can tune that. The box fan itself, we have dialed down to the slowest speed. Overall, this thing turns at about 15 revolutions per second. So what is that? Check my math. About 900 RPM.
I believe so.
Now, it takes about 1 millisecond to draw all these LEDs. So at that rate, we only get to draw about 60 slices of our world with every revolution, and we store 128 slices of the world in memory. So you'll see a little jitter. We don't always draw the same place every time, every revolution. So we're really taking heavy advantage of the persistence of vision effect, that these blue lights are so bright and they really stand out in your eyes. And you really need a dark background to really emphasize that. So that's why we opt for all this black shading, as it really makes it pop, and it really enhances the effect for your eyes. I think what else we might have to say.
That's about it.
Okay. Well, we're going to razzle dazzle you with a little more play. Oh, Don gets this plugged in. Your Arduino. On here, you're going to have to program it and program it and program it and program it. So this is its programming port over here on the side. Make sure you leave a hole so you can actually get the cable. Get your actual programming cable actually on there. So that's why that hole is cut out there for us. Also, we found it very handy to leave the cable right here with the kit so that you always had it during any kind of demonstration. And all source code for this, the plans and everything, they're all up on our website, and we'll put that in the YouTube link comments. So are we ready to roll it back up? So I'm going to turn this around. And we'll get rolled back up. I'm going to slow it way down. Hopefully you can still hear me over the whoosh whoosh. But we're going to slow it way down. We notice you can still see the cube. We found that the rotation speed varied a lot moment to moment. You see it's got a little shake. So the software learns what the rotation speed is from the prior rotation and uses that for the next one for the guesstimate. So there is a sweet spot where the effect looks, the best. We did put in some minimum there. Once we hit that sweet spot, it'll snap in. There we go. Curiously, if you turn up the RPMs too much, because that 1 millisecond is fixed, 1 millisecond to draw the frame is fixed, if you turn up the RPMs too much, then you actually end up with a lower resolution picture because you draw fewer slices per revolution. So there is a sweet spot where you see more of the object. Yeah, Don, I think if we had to do this again, we'd probably custom machine some of the parts.
Heavier frame, better balance on the board.
Yes, heavier frame, better balance. Also, the LEDs are not aligned perfectly with the center, so there is a core, like a core down a pineapple. There, we cannot project the light into that core because the LEDs just don't cross into that region, that volume. I also like to point out that the Pong game is a 2D hack. It's playing a game of Pong in 2D, and you just draw it on some of the slices to make it look 3D. Alright, well again, it's been Don Smith, Wes Baylor, and our volumetric display. I'd like to thank our camera person, Jan.